Hello everyone, I'm Sreeshma Shiv. I'm a second year PhD student in the ECE department of IISc Bangalore. I work with Professor Anda Kumar and Professor Rajesh Sundareshan. Here I'm going to speak about our work on the analysis of finite time performance of a two-step stochastic approximation algorithm that is designed for fair scheduling with rate guaranteed users in a wireless communication system. First, I'll explain what is meant by fair scheduling with rate guaranteed users in 5G, then the mathematical formulation of it, then the algorithm, followed by the results from the finite time analysis of the algorithm. In a wireless communication system, as you may know, most of the aspects are standardized. Five waveforms, coding schemes, data formats, interfaces, all are standardized. So the product differentiation comes from the implementation skills of the developers. Two crucial aspects that are not standardized but left to the design ingenuity of system designers are receiver design and traffic scheduling. Coming to the importance of a good scheduler design, it enables the system to handle a variety of flows while meeting the requirements of each flow and maximizing the number of flows that can be handled to have the best system capacity. Best effort flows are one type of flow that are dominating the network traffic. These arise from file transfers, data backups, video downloads, etc. Such transfers are typically performed over a transport protocol such as TCP, which maintains large windows of packets in flight for each of the file transfer. Fair scheduling among such flow has been widely studied. Standard formulation for such models is to maximize a concave utility function over all possible rate vectors, and gradient algorithm yields the optimum rates. So we use the same idea and extend it to fair scheduling with rate guarantees. One of the practical application of rate guaranteed fair scheduling is in fixed wireless access system. In such network, a subset of users will be associated with a residential or business gateways and require minimum throughput guarantee. Say there are M users in the network, M1 out of M users get a minimum rate guarantee. This can be mathematically formulated as an optimization problem. Theta is the average throughput vector. We choose a strictly concave utility function U and maximize this utility function given the constraints. The first constraint says theta belongs to R bar. R bar here is called rate region. That's the set of all possible throughput vectors that can be provided by any scheduling policy. As you may know, the channel conditions of a wireless system vary over time. Thus, each slot will have some possible rates. An average of all these rates gives rate region R bar. This rate region R bar is proven to be a closed convex set. And the second constraint says theta I greater than or equal to theta I min for 1 less than or equal to I less than or equal to M1. This is the rate guarantee constraint for M1 users. So, a strict concave function maximized over a closed convex set with some linear constraints, this problem will have a unique solution. So, we should have a scheduling algorithm which makes a decision in each slot based on the channel conditions in that slot and the throughput of each UEs at that slot, so that eventually the throughput becomes this unique solution. So the motivation for the algorithms comes from the relaxed version of this problem. This is the relaxed version, and new here is the multiplier. So for we maximize u theta plus summation I equal to 1 to m1 ui theta such that theta belongs to R bar. For a fixed nu, solving this relaxed problems gives theta corresponding to that nu. So here theta nu has x of nu and y of nu in it. X of nu corresponds to the rate guaranteed users and y of nu corresponds to the non-rate guaranteed users. So if nu is updated such that it reaches a new star, such that this x of nu star is equal to theta min, then we have the required solution. That gives the motivation for the primal dual algorithm, where for a given nu, the primal iteration aims to solve the relaxed optimization problem to reach theta nu. Then multipliers are adjusted on a slower time scale to achieve the inequality x of nu star is equal to theta min. This leads to the following two timescale stochastic approximation algorithm, which we call as PFRG-LM algorithm. So here, instantaneous rate R in each slot comes from applying the gradient algorithm in relaxed problem. Choose rate that maximizes the gradient of this function dot R. Then we update throughput in EWMA manner with step size A. These two equations together for a particular nu will cause theta k to track theta nu. Then we update nu on a slower time scale B. Here the index bias is added or subtracted with B time the difference of the throughput from the minimum guaranteed throughput. I'm calling it index bias because this nu, it gives a bias to the UEs with read guarantee if the guaranteed bit rate is not reached. Now we perform the finite analysis of this algorithm. So what we do first is we replace the simultaneous fast and slow update in the two timescale stochastic approximation algorithm with appropriately spaced periodic update of index biases interspersed with slot-wise scheduling with fixed index bias. So we choose a period t equal to a by b. Index biases are updated only at the integer multiples of t, like this. And during the slots in these duration, we schedule UE and update throughput with the fixed index bias of whatever value this has now. So this is validated through simulation, which shows that the behavior of both the original and modified algorithms are closely aligned. We first see the error in the fast iteration of EWMA rate update in the time interval t, which will give how far the iteration at t steps is from the actual solution theta of nu for that nu, and then we find the slow iteration error. That's the error in the bias update from optimal value after n iterations. So the error expressions look like this. Fast iteration error, which we has discussed before, is the error between average throughput over t iterations and the actual solution for that particular nu will be less than or equal to some constant that depends on a and b. Similarly, the slow iteration error, which is the error between nth iteration nu value and the optimal nu value, is exponentially decreasing to some constant value, again depends on a and b. I'm not going into the details of this mathematical expressions. The idea that we can get from here is the finite time analysis gives us a guidance as to the choices of a and b, the step sizes of fast and slow iterations in terms of our requirements on how do we need the convergence to be for our particular use case, and how do we need the steady state error to be for the use case. So depending on that, we can choose an A and B and have the algorithm running for that particular case.